And thanks everyone for choosing to spend your pandemic time with us. We're going to talk a little bit about modeling of a pandemic. And at any time, if you have questions, please write them down so that we can have a great discussion at the end of the presentation. So we're starting with an image that had a lot of implications in March at the beginning of the time that the pandemic was starting up in the United States. And so what we see here are two graphs. In red are predictions of deaths per day per 100,000 population. And on the horizontal axis, you'll see months. So you'll recall that things really picked up here in March. And so this is predicting for the United Kingdom in red, a peak, actually I believe that the United Kingdom must be in blue based on where the peaks are going, but they're peaking somewhere in mid-May and then dying out in kind of mid-July, so sometime around now. Whereas the United States is hitting closer to like 2.2 million deaths per day, kind of in the May vicinity, maybe in June. And this graph had caused quite a stir because this was from model predictions from the Imperial Modeling Group in London. And you may recall reading things about this, maybe seeing things on social media, that there were predictions that over 2 million deaths could be occurring because of COVID-19. And this is assuming that we don't take any sort of action. So this is what things would look like without any social distancing measures, without any adjustments to lifestyle, in two pretty big countries in the United States, namely the United States and the United Kingdom. And this caused almost immediate measures to be taken, including the closure of schools, implementation of social distancing, quarantine, masking requirements, etc. And so here's an example where modeling had a very important impact early on in terms of policy and behavior for these countries and others around the world. So I wanted to talk a little bit about what goes into these models and to show you where some of the outputs have gone with these models as the pandemic has continued. So to think broadly about why modeling would be an important thing to do and why it's perhaps not surprising that we saw models emerging at the beginning of the pandemic. So models can represent real world situations, and they can help leaders make decisions quickly and accurately, and they're convenient, cheap, and low risk. Convenient in the sense that I can sit here at my computer and run some models. Cheap in the sense that, barring a computer, it's not costing a lot of equipment to get these models to run, and low risk, especially in the case that we're talking about in terms of lives. Those graphs that we just looked at, where those peaks were so incredibly high, I mean, that vertical axis was in terms of hundreds of thousands of deaths. That doesn't need to happen in a model. So no one is actually dying. It's just showing what will happen, based on our guess if we don't do anything. So it's important that it's low risk. And before we really wax poetic about models, the important thing to think about is that all models are wrong, but some are useful. And so we'll think about that as we go. When it comes to looking at pandemics specifically, these models are trying to predict, like we saw in that opening graphic, how a disease will spread and the duration of something like a pandemic. So we saw that in those models, assuming we did nothing, with the data they had available in March, they thought that the disease would run its course by mid to late summer. It can also get us to some things that you may have heard about, like reproductive number or reproduction number. So that's the expected number of cases directly generated by one case in a population where all individuals are susceptible to infection. That number is important especially if we think about, I think, news that came out of the CDC yesterday, which said that they thought that most people, if not all, were susceptible to COVID-19. So that reproductive number is important. And these predictions can impact public health interventions, as we have seen with the response to the group from London, where those governments took pretty extreme, quick measures to shut down and encourage quarantine. When you're thinking about things from the math model perspective, there are three big categories that are tending to generate the models that are going into the public health recommendations. Those are statistical models, agent-based models, and what are called compartmental models. In a half hour, I would love to go through all three, but we're gonna focus on compartmental models because they're my favorite and I'm allowed to pick favorites. So ideally, when you're making a policy choice, you should be looking at all three of these models because they all have strengths and weaknesses and they can work together in a good complementary fashion. In fact, some of the things that we're going to look at later in the talk are drawing from things from statistical models. The image that I showed you from the beginning was a combination of compartmental model and agent-based models. So it's very common to use these in conjunction with each other. And they're all important when making decisions. So to introduce you to some notation with the compartmental models, we're going to be assuming that people fall into three categories. And I know we're told to think outside the box, but for right now, we're going to think inside the box. So you're going to be in one of three boxes. The first box is susceptible. So that's creatively abbreviated with the S of T. So that's to remind us that the people in the susceptible box will change over time. I of T are those that are infected, and R of T are those that are removed. So removed could mean that they've had the disease and they are no longer susceptible to getting the disease again. Removed could unfortunately also include those that die from the disease. So people in the removed category cannot get reinfected. And we're assuming that in the simplest case, everyone is in one of these three boxes so that S of T plus I of T plus R of T equals N, where N is the total population. And this is a reasonable assumption if you're looking at something, especially in a short time frame, where it doesn't make sense necessarily to talk about like deaths or births or things outside of the scope of the pandemic itself. In addition to the variables, there are going to be some constants or parameters that we look at in this model. And for whatever reason, you often see Greek letters because why not? So for alpha, that's going to be a measure of how many contacts a sick individual has per day. So that's something that can change if you're looking at social distancing measures, for instance. So if you limit the number of contacts, that would mean you're lowering alpha. And what you're assuming is that since it's the number of contacts per day that a sick person has, if you multiply that by I, which represents the sick people, then alpha I is a way to talk about the number of people per day that are contacted by infectees. But not every contact is going to lead to some type of transmission. So there's some fraction of those people where S was the number that were susceptible and N was the total population that are actually going to be susceptible to that disease. Beta is going to be, again, a constant, and that's going to represent the recovery time for people that are infected with the disease. So that's the number, it's the fraction of the infected group that will recover during any given day. So these are both going to be positive. And practically speaking, looking at the reciprocal of beta is going to be important because that can represent the average duration of an infection. And that's something that's perhaps easier to measure or easier to get information on. In a minute, you're going to see Noelie take us through this model, replicating a project she had done in class with me in the spring. And you'll realize that the parameters are actually very difficult to find in practice. So we can put all of this information together into this schematic which represents our model. So again, everyone is in one of three boxes. I'm looking at this as fractions in the population. So S, that little s is the fraction of susceptible people in the population. The little I is the fraction of infected people in the population. And the little r is the fraction of removed people in the population. What we can see is that everyone is in one of three boxes. And with the susceptible box, no one can come into the susceptible box. You can only leave that box. So we see the arrow to the right leaving the box. How do you leave the box? Well, if you leave the box in this simple framework, what you're going to do is become sick. How do you get sick? Again, that was related to that alpha that we talked about a minute ago. So you're going to come into contact with people who are sick. That interaction, since this is a contagious disease, is going to lead you to become sick. So the things that could lower that transmission rate that is involved with the alpha could involve things like social distancing so that the sick people have fewer contacts. Another way that you can reduce the probability that these contacts result in an illness is to do something like wearing masks, where even if you're in contact, the transmission isn't going to happen in the same way. Once you're sick, so looking at that middle box, again, you only became sick by coming into contact with someone who is already sick. And the only way that you're going to get better or removed is to wait for the disease to basically work its way out of your system, in the simplest case. And then the removed category, we see there's only one way in and there's no way out. So in, again, this very simple schematic, the only way to get to the R box is by having been susceptible, getting sick, and then being removed. Another way that you can simulate some decisions from a public health perspective could be to look at vaccines, for instance. And so one thing you can do with vaccines is to assume, instead of having to go through that flow chart, that you just start in the removed box. So you're not even susceptible to begin with. So that's one way that, I guess it's another way you can start. You can get to that box is if you start in that box through some mechanism like a vaccine. We had talked a bit ago about some of the decisions that people can make once they look at a model. And one of those decisions and important pieces of information would be the basic reproductive number. So each model that you look at has a different way to calculate or approximate the basic reproductive number. For our model, that's going to look at the ratio of alpha and beta. So those were the two parameters we had for our system. Remember, alpha had to do with the number of contacts that an infected person made per day. And the 1 over beta we said was a useful thing that looked at the duration of the illness. So if I, instead of looking at it as alpha over beta, if I think of it as alpha times 1 over beta, then I can see that that must be the number of people, on average again, to whom one infected person will pass the virus. So if I think of it like that, if this constant R0 is bigger than 1, the disease will propagate in the population, meaning it will go on and on. If it's smaller than 1, then the disease will disappear from the population. And obviously that would be the desired outcome. For me, sometimes it's easier to think in terms of pictures and not Greek letters. So this is showing basically what we think about with that R0. So on the left, if the R0 is 1, we see one sick person, oddly represented in purple with a big exploding virus behind them. And then they will cause one secondary infection, and then that person will cause another, and so on and so forth. So we can see it continuing like that. If the R0 is 4, so remember we said that R0 bigger than 1, less than 1. So 1 was really the sort of threshold that we were aiming to get below. If you're above that threshold, so if your R0 is 4, which is what we see on the right, then there's one sick person here, and then they're going to cause 4 secondary infections. And then each of those people are going to cause 4 more secondary infections, and on and on. And so we see a whole lot of purple mess, even just a few kind of generations into the disease process. And that's bad. And so now Noelie will discuss how she used this framework in our class.
So in our class, our job was to model basically how COVID-19 is spreading and just see how it's affecting the population. I decided to look at the Diamond Princess cruise ship because cruise ships are ideal experiments of a closed population for the SIR model, because you know exactly who is there and you can measure everyone, not just those with severe symptoms. So if someone's asymptomatic, they'll still get tested and you'll know if they're positive. In modeling the Diamond Princess cruise ship, we know the population was 3,711 people, and a total of 711 people were infected. We assumed that one person was infected at the start of the cruise because you don't really know how many people came in sick, so we had to assume. We assumed that people were infectious for 5 days, so beta is 1/5. However, that's a very low estimate of how long people are infectious, but it's really hard to find an alpha, so beta is easier to find, so we just kind of lowballed it a little. We found that the R0 was 2.28, and which we estimated from a statistical study, and so therefore alpha, which as I said was hard to find, is 0.1629. So this is looking at the actual data and the model of our data, where the x-axis is the date in days or the time in the model, and the y-axis is the percent of people that were infected. In total, about 19% of the population was infected. We looked at this over the course of 1 month of February 2020, and as you can see, it starts out, there's about 5 days before the infection really starts, and then it climbs from about February 6th to about February 22nd, and reaches its peak at about February 27th, and sort of evens out from there. Again, our R0 was 2.28, which you can kind of work backward from to find the alpha, as mentioned in the previous slide. So I looked specifically at flattening the curve and seeing what you can do to try to. Looking specifically at social distancing measures, so kind of changing the R0 while keeping beta the same, which means we're also changing the alpha because beta is staying the same. And alpha sort of takes into account the number of people that are in contact, number of people you were in contact with, and the chance they can infect people, which means it takes into account quarantining and also wearing masks. Because if you're quarantining, you're not in contact with as many people. And if you're wearing a mask, it's harder for you to infect them. So we assumed same conditions as what happened in reality, but we changed the R0. So in this, on this slide, you can see two figures. Figure 3, which has an R0 of 5, and figure 4, which is an R0 of 1.5. We know these are kind of extreme numbers, but the point of modeling is to see what happens if you hit extremes, because likely what's going to happen is going to be in the middle. So on these graphs, the x-axis is the time in days, and the y-axis is the percent of people. Everyone is represented in these graphs. The blue line is the number of people that are susceptible to the illness, so it's going to start off as everyone and then decrease. The orange is how many people are infected, so it's going to start off really low and increase and then go back down because people are going to become removed, which is the green line. So on the R0 of 5 graph, the peak infection happened at about day 12, and over 40% of the population was infected, whereas on the graph with the R0 of 1.5, the peak infection happened about day 70, and less than 10% of the population was infected. This means that the lower your R0 is, the longer time it takes for the infection to run its course. And while we recognize that 1.5 is bigger than we really would like for an R0, it still has a really good impact because it takes a lot longer for the virus to run its course, and very few people are infected. So, some basic conclusions. If you don't interact with a lot of people, it's a lot harder to spread a disease. So, social distancing works. So does wearing a mask. And you can also kind of see on those last two graphs that as the R0 decreases, the curve flattens, but the infection stays in the population longer because, you know, you're not interacting with as many people, but the disease still has to do its thing.
So that was looking at the basic framework with the compartmental models, and hopefully you get a sense for the kinds of assumptions that go into working with that model and an appreciation for the difficulty and therefore the interestingness in coming up with things like the parameters. We wanted to close with the second application of the modeling to COVID-19, and this is based on a paper that came out in June, and this is looking at age-dependent effects in the transmission and control of COVID-19 epidemics. So basically, this is one of the papers that had gone into decisions made by the American Association of Pediatricians when they were making recommendations as to whether people should be returning to school face-to-face or not for fall. So the goal of this study was to estimate age-specific susceptibility to COVID-19 infection and age-specific fraction of infections that develop full clinical symptoms of COVID-19. And if that's the goal of your study, you can see some things popping up right away. So again, looking, as the pandemic has continued, we've seen that susceptibility to the disease seems to be age-dependent, and so will the model bear that out? You can also see some keywords popping out like fraction of infections, susceptibility, and so that's leading us to think about those types of variables we've already been considering in the basic framework. And I know there are a lot of letters here, but it's going to be fine. Remember, in our basic model, we had S, I, and R, and that's what we have here. Here's S, still the number of susceptible people. A whole bunch of I's here, and R at the bottom. So what's different? Basically, we have more boxes to put people into. One new box is the E box, so that's the number of exposed people at time t. And then what's going to happen with the infection is that it's going to kind of take one of two routes. You're either going to develop the full kind of clinical infection, which is presenting with the scary types of symptoms that we've read about, or in some cases, unfortunately, may have experienced more firsthand. And that scary route is going to, so you're going to be susceptible, you're going to be exposed to someone who is sick, you're going to develop pre-symptomatic symptoms early on, and then that's going to lead into that full clinical infection. The alternative is that you are susceptible, you get exposed, and instead of presenting with the full set of symptoms, your symptoms may be more mild. So this could so that's what the I sub S is standing for. That's the subclinical infectious group. So that could include people that are asymptomatic. That could include people that have more mild symptoms for whatever the reason. And then R is still the number of removed people at time t. So we're basically just adding a few more boxes, which would make sense to take a basic framework and make it a little more complex once we know more about how the disease specifically is working in our population. The schematic that goes along with that is here. And just to walk you through that, so again, you're going to be susceptible. You're going to come into contact with someone who's sick, and that's going to lead you to be sick. You've been exposed, but you may not realize it yet. And then again, there's one of two routes you can take. The top route here is the one where you're going to develop full clinical symptoms. The bottom route, which if you have to choose one of two routes would be, I guess, the better one, perhaps, is the asymptomatic route or more mild presentation of symptoms. both will lead you to the removed box. Just a quick note here, you'll notice the subscripts with the eyes. So they were doing this at different age groups, as we'll see with the conclusions. And then in terms of the transmission, these Ds that we see in a lot of the places are no longer constants, because that was one of the drawbacks in the basic framework. These are actually going to be functions that depend on time. And so that's, again, a way to think about how you can change that alpha or the R naught in more real time. Findings from this study, they found that people who were under 20 were roughly half as susceptible to infection as those over 20. And again, interesting, again, this is just a little model world, but we can see that it resonates with what we've experienced during the course of the pandemic. They also found that 79% of infections are subclinical in the 10 to 19-year-olds, meaning that's the subclinical, meaning the group that included the asymptomatic people or the people with more mild symptoms. Whereas in those who are over 70 years of age, the model predicts that 31% of the cases will be subclinical. Some things to think about when looking at their methodology. The model was fit with data from China, Italy, Japan, Singapore, Canada, and South Korea, with data collected from early stages in the pandemic. If this is published in June, then that means they must have been gathering the data and writing this up pretty quickly. So yes, you'll notice that the model does not include data from the United States, and that these countries represent a variety in terms of composition in the population, and also some variety in terms of those governments' responses to the pandemic. The authors also point out that more data is needed in understanding if and by how much subclinical infections contribute to transmission, because their findings are that there are some differences in the age structure as to percentages that will develop subclinical infections, but there's still, because this is a relatively new disease to understand, a need for more information to understand how the infection is transmitted in these more mild cases. Some of the implications to that then would be, based on what they said, that school closures might be less effective than for other respiratory infections. And I think that was something that, again, you would have heard about in the news, that, you know, oh, perhaps it's okay for the schools to go face-to-face because they were finding that the younger population was less likely to develop the more severe symptoms. Now, you'll notice in the model, there aren't, you know, that still doesn't necessarily account for the fact that there are teachers and staff in the school who would be older and therefore in those higher risk categories potentially. Another point that they make for the implications is that the countries with a large number of children might need to account for decreased susceptibility and severity and burden projections, which would be an important outcome. So conclusions from what we've seen with the modeling, and then we'll be ready for questions. Modeling is important to predict the spread of the disease, the duration of the disease, the impact of control measures. And again, it's important for those predictions because of the low risk, low cost, both in terms of money and lives, that we can do with the modeling. And by just changing some things, we can mimic what would happen if people change their behaviors or make different decisions, and make some interesting conclusions that way. Another thing that's important to think about is that better data lead to better models. And that was certainly the case with what the authors were discussing in their paper that I had just pointed out, the one that was published in June. And that point is one in which, you know, it's concerning to me in the news when we hear of things like the CDC being stripped of their data collection abilities. So the more data we can collect, the more testing we can do, the more places that can responsibly handle the data, that'll lead to better models and better outcomes. And another thing to think about is that it's important to not underestimate the value of interdisciplinary thinking. These are mathematicians working with epidemiologists, working with biologists, working with sociologists, you know, like working together to really come up with the best outcomes for everyone. So for further reading, because I know you'll be anxious to do so as soon as possible, the first two here talk about generally the SIR type models that we looked at and some of the things that we talked about with the reproductive number. Noelie's work with the cruise ship is in the next two papers here, and the data she used was from Johns Hopkins data source. And then the paper I just talked about is here. And this one is a nice sort of overview of, again, thinking about the different types of models out there and how they're used for epidemiology and COVID-19. Thank you.